Good evening, everybody. I'm John Berry, and you may know me as my name because I recently retired as editor of the Professional Geologist. And we're hoping that we in the A section are hoping that this will be the first of a long series of on the third Tuesday of every month at 7 p.m. And I'm going to be giving the first view on the geology of Central Texas. And this lecture takes it up to the end of the Paleozoic. And the next one is follow with the Mesozoic and the Cenozoic. We will probably shift the December meeting to the second Tuesday because the third Tuesday is the 21st, so a little close to Christmas. So my outline is here. I start with a bit about the geology of Austin, and that leads into, and then a section on the history of the conglomeration and breakup of supercontinents that affect the Central Texas area. And then if I haven't gone over my time by then, I might make a few general points about the growth of continental crust through time and why mountains form in the same places, why new mountains form in the same places as old ones. So here's the tectonic map of Texas. And the places I'm going to be talking about in this particular talk are numbered 1 to 4. And that's the Llano Uplift in the center here with its Precambrian rocks labeled as number 3. I'll say a couple of words about the Marathon Uplift. And number 4 is the buried Ouachita facies, the thrusted rocks of the Ouachita orogeny. 5 and 6 will be left until the future lectures. So this is a cross-section through the geology of the Austin area, highway map of Texas. So some of you may even have this cross-section. And the vertical exaggeration is about 50 times, 60 times, and you can see the scale on the bottom. So what I've done here is join up the unconformities on either side of the uplift. The top of the Precambrian, which is in this sort of dark red color here, and the unconformity, the top of the Cambrian, which is here, then the unconformity at the top of the Mississippian, base of the Pennsylvanian here, and the pre-Cretaceous surface, which Pete Rose is going to be giving a tremendous paper, GCAGS geoing up in a month. What I'm going to do is show you sections flattened on these surfaces. So here we flattened on the base Cretaceous, going backwards through it. And you can see here, this is the very rugged unconformity on the top of the Precambrian, with the lower Paleozoic covering it and the upper Paleozoic over that. And then proceeding from southeast to northwest, these thrust sheets of the Ouachita facies of their lower Paleozoic deep water rocks, basinal rocks that are thrust over the shelf equivalents here and over the upper Paleozoic as well. And there are at least 2 of these thrust sheets, each one, of course, bringing slightly more metamorphosed rocks further west. I probably have these a bit thin. This is very schematic anyway. The green line is the current surface. So you can see that an awful lot we don't see these rocks at the surface at all. They're buried about 1,000 feet beneath Austin. the nearest ones. And where they're dashed, they're eroded away completely. So then going on to the next surface, here is a section flattened on the top of the Precambrian with the present surface in green and the Cretaceous surface in blue, and everything that's eroded away in dashed lines. And you can see there's been quite a bit of erosion of the Grenville basement and almost complete erosion of the thrust part of the Paleozoic sequence. Over here, we start seeing the Paleozoic sequence dipping gently to the west. So what we have in effect is parts of two orogenic belts. Grenvillian basement, which is high-grade metamorphic rocks, thrusted to the north and intruded by syntectonic and post-tectonic granites. And then on top of that, the Ouachita, the outer reaches of the Ouachita orogeny. And that brings into play of these recurring, the plate tectonics naturally, all the cratons and consonants to make a supercontinent every once in a while, and then it's unstable, so it eventually splits up. So we get rifting here, and this is due to heating at the base of the crust. And what I'm emphasizing here is that rifting is preceded by a regional 700,000 kilometer updoming of up to 2,000-3,000 meters. And the idea in my mind is East Africa, the Red Sea, the west coasts of South America and Southern Africa, which all have huge escarpments at their trailing edges. So as the ocean forms, things cool down there. We still have a hot oceanic crust in the ocean, and then eventually the ocean gets so wide that we get subduction. The subduction closes up the ocean, the continents crash together again, and there's this huge thick continent here, which is sinking down into the mantle isostatically, and that causes it to get much hotter at the base, and then it starts, and it gets rapid erosion, and it starts to rise rapidly, and you get decompression, melting of the mantle, adiabatic melting of the mantle and the base of the crust here, and that leads to the recurrence of this unstable situation of a high area with sloping flanks, which has very little friction with what's underneath it, and is very warm, so it tends to split up. Some of the things linked to the Wilson cycle are the climatic cycle, where we have, during periods of supercontinent existence, we tend to have glaciations, extensive glaciations. And when they break up, the climate gets warmer, so we get the late Cambrian Ordovician, lots of carbonates, and then the climate cools down again as the next supercontinent gets together, and then it tends to warm up again. So we get, after that breaks up, so we get the Jurassic and Cretaceous warm periods before going down into our most recent period of glaciation. And this continents, they're riding high. So sea level is in fact low. And this is the scale on the left is percent submerged of the continental platforms. And you see this hugely submerged during the interglacial epochs and very exposed during the supercontinent glacial times. And here's the Vail curve, which is roughly the same, the eustatic curve. And then this is the amount of granitic intrusion, which seems to peak at about the time the continents are in the initial stages of drifting apart. The other thing is, some people suggest that the Wilson cycle is associated with major evolutionary events. So here we have the eukaryotes beginning at the time of the very earliest the supercontinents, and then the sponges and things coming in at about 1500 million. This is the Columbian supercontinent. The Metazoans beginning at the time of the Rhodinian supercontinent, the Grenville orogeny, and then things with skeletons at the time of Pangaea. After that, at the end of the Precambrian, and then the mammals coming in at the time of Pangea, or just after the time of Pangea. So this is a very, and it's not really cyclic, it's quasi-cyclic. So the oldest supercontinent was Valbara, 3.1 billion years ago. It was smaller than Australia and consists of the Pilbara. I'll show you a map in a minute. The Pilbara Craton and the Cartval Craton. Kenorland was much bigger, 5 times the size of present North America. Columbia was sort of modern. It had everything in it. Rodinia was really well documented, very much a precursor of Pangea. Pangaea is a bit questionable. Originally, it was thought to be better documented than Rodinia. Now whether it really ever existed is queried. I spent my early career in Africa, and you query it if you were in Africa. I think querying the existence of Pangaea is a Laurasian point of view. Then Pangea, the 300 million that broke up after 100 million years to give us Laurasia and Gondwana. You'll notice there's 400 million years here. There's a gap here of twice that, 900 million years. A slightly longer gap here of 700 million, longer than 400. And then it's 500, 300 years, and we're going into a new supercontinent cycle with Asia, India, Europe, Australia getting ready to, and just leaving out the Americas and Antarctica. So about another 350, 400 million years, say, after Pangea to the next one. So it's quasi-cyclic, but not quite cyclic. And there's probably one missing in this gap. Sorry, this gap. So here are the actual examples. The Valbara at 3.6 to 2.8, consisting of, oops, what's gone wrong with my machine is, I want it to. Cartval and the Pilbara in Australia. Here's Kenorland, and already we have these cratons, a lot of cratons taking part in it: Siberia, China, Australia, Antarctica, Brazil, Baltica. Only India that we know about that's not. And of course, new cratons are forming all the time. So here's Columbia, where we really have most of the ones that we know about. All the ones in Laurentia here, Greenland, Siberia, Baltica, Amazonia, India, North China, South China, West Australia, Kalahari, etc. And very modern looking in the list of and the shape. And here's a long subduction zone like the one we have now along the American. So that brings us up to Columbia. So yeah, that is Columbia. And this is a rather gaudy version of the assembly of North America, and you've probably seen diagrams like this before. But we have the core in the Superior craton here, and then almost equally old cores in the Slave and the Wyoming and Greenland, 9, and over in Baltica, the Karelian. And you can see that Baltica is really a bit of North America. It has the same sequence of greater than 2.5, and then the yellow 2.0s, and the blue 2.0, 1.8 to 2.0s, and then the Grenville and the Caledonian. They're all there in Baltica. Then after this assemblage, we start getting to Central Texas. We at 1.8 to 1.6, the Java-Besatzal terrain joins the assemblage, and we're on the edge, just off the edge of that terrain. So I think we can regard the Precambrian rocks in the Llano uplift as being the passive margin sediment wedge related to the erosion of the Yavapai-Besatzal edge of North America. Then, of course, we got the Rodinia supercontinent, which was formed by which crashed into Laurentia here, and of course the Grenville orogenic belt. And this is just part of the Grenville orogenic belt. And then we had that split apart down the middle, so that we're just adding a little bit to North America each time, but the splits, the rifting is always parallel to the margin. And we get the Ouachitas and the Appalachians as things crash together to make Pangea. And I've given that in table form here with the supercontinents out in capital letters to the left, and the terrains and rifting events here in the center, and the in yellow, starting with Colombia. So here's a picture of Rodinia on the left at 1.3 to 1.0 gigaamps. And throughout this talk, a red star sometimes has a yellow margin or some other margin to make it stand out, is where Central Texas is. On this, Central Texas is in this angle here. On this other map, it's got a blue core, but it's down on the edge here. The blue stars are areas that I've either lived or been associated with in my life. So we have a blue star here in North Queensland, Australia, which is where my parents spent the last 30 years of their life. And there are two alternative positions for Australia here. But you can see that the Grenville belt starts in Antarctica, then matches up with West Australia, goes through the center of Australia, leaves out through Eastern Australia. This little patch here where my cursor is next to Gorla, that's the Kalahari Craton. Then it goes through Mexico, the Oaxaca terrain, all the way up the east coast of Laurentia and into Baltica, and it actually goes further into Central Europe. The red things here are a dike swarm, because the authors of this paper thought that there was a hotspot up here in Laurentia. The black area is the failed mid-continent rift, which is of Grenville age. 200 million years later, what's happened is that Baltica has moved down until it is opposite the Greenland and maritime Canada, and it's rotated. And Amazonia has also rotated. So we have these black things which are pieces of the orogenic belt, which have rotated away from the main suture. And at the same time, there have been some rearrangements here, and Australia, they've decided is really up in this corner at that time. And in Zambia at the beginning of my career, and Zambia was about as far away from Austin now as Austin is from the peninsula in Mexico, in Cancun, whereas it's a lot further away from northeastern Australia than it was 200 million years early. And I think one of the amazing things about plate tectonics is these amazing juxtapositions which happen. When Wilson, the idea of a cycle, I think he originally had the idea the oceans opened up and closed again much the same as they were. Well, in some ways they do, but in other ways you have these massive arrangements. So here's the Grenvillian in North America again, going up into Baltica. Here we are, it's the red star here. Here's Mazatzal Yavapai, and this terrain here, which is this author distinguishes from Mazatzal Yavapai as being a little bit younger. So we're stuff that was basically originally sediment derived from this area, and then was metamorphosed in the Grenville origin. And then after, by 900, the Grenville the Verdinius continent was getting unstable and things were beginning to weaken. And by about 650, things drift off away from the other side of the Grenville origin, and it was Amazonia that was here actually, and it drifts away. And so this is the early Paleozoic, lower Paleozoic continental margin, just running up more or less what we think of as the eastern edge, southeastern edge of the Grenville origin, but there's more Grenville that was on Amazonia, so it's not quite as. And the breakup of Rodinia leads this rather doubtful or questioned assembly of the next Pangaea, the next supercontinent. And people think it happened because there was an 800 to 700 million year rift between Gondwana and these pieces, between Laurentia and these pieces of Gondwana. And then there was a later 600 to 550 million year rift that separated Laurentia from Baltica, Amazonia, Rio Plata. So that's basically the split down the Grenville orogeny. Trouble with this 600, it undoubtedly exists, but the trouble with that is that in Africa, you had the assembly of Africa going on at the same time, the Pan-African orogenies, starting at 700 and ending at about 550, all through Africa. And here, but before I get to that, here is the ice cap of the Cryogenian period, which originally was thought to, people said, well, was started at 860 million because that's when the first big glaciation was. But then it was limited to 720 million to 635 for reasons I don't understand. But that leaves out one of the largest phases of glaciation, which was around 850. And you can see here that the continent is actually over the pole, South Pole, and very extensive ice cap. I think this is a minimum personally, because I know that areas of, that there's some glacial material in Australia, there's lots of glacial material in North Europe, and there's a lot more glacial, I think, a lot more glacial material here than in Africa than they show here. So the Congo Craton has got a very, very, very extensive glacial marine, two very extensive glacial marine episodes. So it's some idea of Pangaea, but as I say, it's controversial. It's regarded now as the semi-intermediate stage between Rodinia and Pangea. And this is what people think it looked like. And here's Texas. And here's where it really started to break up. Triple rift junctions between Australia, Antarctica, and India, and between the Congo Craton and the West African Craton and the Brazilian Craton. So this is the failed arm of the, more or less in the same place as failed arm of the Benue Trough. And this is where the South Atlantic and the Mid-Atlantic are. Another view, an Africa-centric view of Pangaea, which I prefer, is this one here. And you can see with Africa in the middle, you have all these dark brown areas, which are all these Pan-African orogenies. The Lufillian, which includes the copper deposits that I was working on, the San Francisco, which also has very similar rocks and also some copper in Brazil, Rio de la Plata, the West African belts, the sort of proto-Mauritanides here, a belt going through the Sahara here, and then the whole thing ends up with this tremendous continental collision along what they're calling now the East African origin, and we used to call them Mozambique. But after that happened, then you had these green areas here, which were which had a subduction zone beneath them, and in particular, I know that along this quadrant of the Pan-Ocean coast, there were 7 island arcs added between the end of the East African origin and the breakup of Pan-Ocean. So, so everything from about the Red Sea onwards is a sequence of island arcs welded to the continent here. And we've already spoken about the glaciation. So then we got to Pangea, and so Pan-Ocean, or whatever it was in reality, the Iapetus Ocean here, that with Laurentia, and we're on the eastern tip in this projection. Here's the Avalon terrain, a sliver of continental material. There was an island arc here, which crashed into Laurentia in the Tectonic, and this is the mid-ocean ridges. So after that crash settled at around 495 million years ago, then Avalonia broke off. We got a back arc basin here, or 2 back arc basins here, and the Avalonia terrain and these upper allochthonous units broke off and started crossing the ocean towards Laurentia and Baltica. And the ocean behind them is then called the Rheic Ocean. It got bigger and bigger and bigger. The Iapetus disappeared, and we got the orogenies in this area, northern Appalachians here. Then around the final collision of the allochthonous terrains up in the north here with Baltica and west the Maritimes, and finally at around 350, the complete closure of the ocean, the formation of the Appalachian Mountains, particularly the southern Appalachian Mountains, closure, eventually the closure of this ocean here. So the picture in North America looks like the bottom part here, where we have the Acadian orogeny. This is the northern part of North America. So we have the Acadian orogeny, Avalonia, the Greenland calcedonides, the Scandinavian calcedonides, the North European Polish calcedonides here, and the mid-European ones that go through southern England here. And then finally, we end up with this big collision of the Alleghanian orogeny and the Hercynian Variscan orogeny between Alleghanian and North America, Africa to North America, and the Variscan involving Europe. So that's the assembly. And I use this picture of Pangea because in some ways it takes me a while to appreciate what I'm looking at when I look at these supercontinental reconstructions. You know, I have to figure out which every blob is, and they're usually indicated by a couple of letters. But it enables a much more intuitive understanding of going from Thailand and Indonesia here through China, Russia, and so on, and Africa sitting in the center here, surrounded by all these pieces. North America forming the western boundary with this long-lived subduction zone there. And I'm sorry, but I'm doing that again. The red star is Texas, and the yellow arrows here represent the drainage from the Appalachians. One thing that you can see in all these reconstructions of Pangea is that it's very narrow here and here. The Arctic Ocean is already there. It's a lake, but it's one of the most long-lived oceans because it hasn't had a lot of subduction in it or around it. So it's a big lake, but there's only a narrow piece of continental connection here. And it's not so wide going across where the Great Lakes and the northern United States are either. So, and there's this huge mountain chain, of course, the Appalachian Belt that goes all through here in the Ouachitas. And it's in a howling desert. This whole area is a howling desert, as we know in the Permian. So one authors, well, a lot of authors in North America working with zircons, this very extremely accurate analysis of zircons, have decided there's a river carrying zircons from the Appalachian Mountains across the top of the Mississippi embayment because it wasn't there, and then through the western United States and into the first into the Permian Basin and then out to the coast, a longitudinal river. So the Permian Basin is filling with all these Pennsylvanian and Permian rocks derived from the Appalachians, largely derived from the Appalachians. I have a feeling there was another river. I've done a lot of work on the history of the Appalachians, and I have a feeling there was another longitudinal moving up in this area where all these lakes are here, which are a series of Triassic basins filled with enormous amounts of halite and even potash salts. So, and they probably didn't flow all the time. It was too dry, but there's a series of Triassic basins that go all the way up the Appalachian chain to this area. And of course, it was nearly the easternmost of all these rift basins in the Triassic that failed and led to the breakup of Pangea. So bringing all that back to Texas, we have in the area here, between the Llano Front, which is the front of the Grenvillian, or a local name for the front of the Grenvillian orogeny, and the Ouachita Front here, the Ouachita Front makes this big bulge around the Llano Uplift. And I have a feeling that if the Llano Uplift weren't there, these two lines would be parallel through Texas. Because I think the Llano Uplift has risen so much that there's a strong possibility that those naps that come up from the east and exist right underneath Austin actually went right over the top of the thing, but they've been eroded completely away. So the rocks, the Precambrian rocks comprising this area begin with the valley spring domain here, which is supercrustal rocks, and they have been overthrust by the Pack-Saddle domain. This is according to Sharon Moser and her co-workers, and that in turn has been overthrust by the Coal Creek domain, which also has internal thrust. The Coal Creek domain apparently is an island arc that accreted onto the Llano area or Texas area from the south. It contains serpentinites, and it largely is consisted of very amphibole-rich rocks, very mafic rocks. The Pack-Saddle is supercrusted rocks that belong to North America, and so is the Valley Spring domain, with perhaps some continental basement from the Mazatlal terrain included in this. You can see this 1,366 million year block. The whole thing is intruded by syntectonic granites by post-tectonic granites. What you will notice, though, in spite of these low-angle thrust faults being shown here, is that all the dates in these overlap. You have 1298 here and 1253 and 32 here, whereas this, if you stayed with classical geology, this should all be older than the underlying thrust sheet. And the same with the Coal Creek. In the Coal Creek, you can understand it because it's an allochthonous exotic terrain that was welded on. So it formed maybe 200 or 300 million years before it ended up as part of the Llano uplift. So you can understand why that is older and has a different history with different dates. So here's the outcrop map, the detailed map of the region, showing these belts with the Coal Creek and the serpentinite down here. Here is largely the Pack-Saddle domain with the Valley Spring gneiss, which is this one, and the paler pink, and the dark red is the post-tectonic granites, and this sort of funny here, I don't know what to call it. This is the syntectonic granites, all folded and mushed. And most of these faults, to me, look like strike-slip faults. This is a strike-slip pattern, and this looks like an extensional flower structure, drop-down basin here. And definitely there's strike-slip up here. We've got, 25 kilometers of strike-slip affecting these wedges of Lost Creek gneiss. So Sharon Moser and her work and her colleagues believe that the impinging continent came in from the southwest. So this is the trend of the local trend of the continental collision. I've had a bit of difficulty envisaging that because the local trend is much more east-west than northwest-southeast. But one can see that it's overall the structure is anticlinal. These things in the middle are generally a bit younger than the things on the outside. So to sum up, the final assembly of Pangea in Texas is we have these early Laurentia, including the Llano uplift area, which is here, consisting of much older that are represented in the grays and pinks here. And then we have the failed arm of the mid-continent rift in green and the Grenville orogeny in green. And we have the Marathon Washita orogenies here in these colors, and behind them the Africa, South America, and the Permian highland of maybe questionable origin in Florida. And several authors have, this is based on the zircon work again, a lot of which is done at UT, postulate a river running through all these fallen basins, the Appalachian Basin, the Black Warrior Basin, the Anadarko, the Fort Worth, and into the Permian Basin, where it either dried up and periodically overflowed to the ocean just to the west. My thought is there was another river, perhaps starting somewhere here, that ran the other way. They have to run one of these two directions because they can't get to the sea any other way. Here's the paleo equator. Here's the, that star shouldn't be there. It kind of got stuck there, couldn't get moved it. But here's the Permian Basin, full of Pennsylvanian and Permian sediments brought in by this river. What this doesn't make quite so clear, but it is clear, is that the ancestral Rocky Mountains here are at least partially formed because there was this bulge on the impinging South American continent, North America apart there. And the Permian Basin is actually the part of that was partially overridden. It's this combination and ancestral Rockies. And if you look at a regional map, you can trace the series of basins and gravels and horsts that connect with the ancestral Rockies. I didn't realize this for a long time because maps of the Delaware and Midland Basin always end here and never show the connections to the north. Here's a little cross-section sketch showing the longitudinal river and the rivers going out, and the Appalachian Mountains here and Laurentia going down here. It also shows a monsoon. I'm not sure how much monsoon there was. And then beneath it is this incredibly complex cross-section drawn by one of my mentors at Shell, showing it's a cross-section through the Ouachitas in Arkansas, where this yellow line is, and it shows that ramp of 10 degrees dip here and 6 degrees at its tail end here, that goes on down off the picture here into basement. So this big lump here is a basement duplex that's being pushed up along this thrust fault, major thrust fault. And in front of it, we have all these complex structures in the Pennsylvanian carbonates and so forth, as well as less easily resolvable structures in the Mississippian and Cambridge Division. And on top of it, there was clearly some resistance because things verged the other way. And these structures were carried in passively on the back. If we could see the structure of the Washington Central Texas, that's an idea of what they might look like. What I'm suggesting, where we have the Llano uplift, we were originally still in this region, but the uplift on the Llano was enough to get this whole package eroded off. So this just is to sum up the time periods, because I know that it gets very confusing. On the right here, we have the Precambrian with 100 million years represented by this scale bar here. So it's 1/14 of the scale on the left. And all of these Precambrian rocks in the Llano uplift are between 1,400 million years old, and rocks on uplift. So that's the basement of this. And we have the Coal Creek Island Allochthonous, the Coal Creek Allochthonous Island arc coming in, which is among the oldest of these rocks. That leads to high pressure metamorphism as stuff goes partially down the subduction zone, and then things lock up and mountains rise and things are uplifted, and we get high temperature, low pressure with a lot of granite intrusion leading, and that mountains get rapidly eroded away. Then we have the snowball earth, which there's no evidence for in this area that I know of, followed by rifting at the end of the Precambrian in Texas and Tennessee. And I mentioned Tennessee because if you were to go there and visit the Great Smoky Mountain National Park, you'd be traversing 70,000 feet of plastic sediments derived from the edge of the North American continent. So it's analogous to the Llano uplift, except we can't see any of it east of the Llano uplift. So on the left-hand side here, we have the Paleozoic with a much bigger scale for 100 million years, and this long-lasting Appalachian orogeny. The mountains were eroded away by the beginning of the Grenville Mountains were eroded away by the beginning of the Cambrian Ordovician, and then you have this Tectonic orogeny where an exotic terrain collides the Acadian, which is where the one in Newfoundland hit, and then the continental collision in the Alleghanian orogeny. And I haven't mentioned that up in the east, you have an island arc, just like the Coal Creek Island arc, welded to in front of the African continent as they collide, and that is left behind on America, that's the Carolina terrain, when the Atlantic opens. So then the mountains are eroded away again in the Permian and Triassic, and the updoming starts, and we get the whole thing beginning to repeat itself for the third time in the Triassic and Jurassic. And that's the end of my talk, I think. And I'll entertain questions. Thank you very much. Okay.
John, we have a question of, can you speak to example of Coal Creek Island Arc in Van Horn, Texas?
You know, I don't know much about the Van Horn area. I'm going to, the AIPG Texas is going to run a field trip there this spring. And after that, I hope to know a lot more. So I'm sorry, I really don't want to talk about that, but I do know that there are some older rocks in the Van Horn area.
If anybody wants to unmute and ask John a question, you can do that as well.
Yeah, you can do that. I'm happy to do that.
Hello, John. This is David. You mentioned that you worked in copper properties in the Congo. Where would you look for copper around Texas and all this geology you're talking about?
I don't know of any copper in the old rocks in Texas. There are strata-bound copper deposits, small and insignificant ones, in the Mesozoic succession in, I think, mostly in northwest Texas. Michael Campbell can probably answer that better than I can.
Yeah, John, you're right. But a lot of that is so minor that it's sort of hasn't gotten much attention. But the minor uranium in North Texas, for example, that looked like yellow flour, has been overlooked for decades. And until somebody looked at it recently, or fairly recently, did they realize that that is some sort of a resource. I doubt if it's going to be much, but the fact is, there's a lot of work that still needs to be done on strata-bound mineralization, and it's just not getting done these days.
The big strata-bound deposits in Africa occur in what the oil geologists call the pre-rift succession, and they occur where the basal oxidized quartzites and sandstones and conglomerates filling the rift are overlain by lagoonal, very organic rich lagoonal deposits and stromatolitic deposits at the bottom of an increasingly marine succession. And all of the copper, the big copper deposits, I think that the same sort of general scenario applies to white pine in Michigan and applies to the Kupferschiefer in Europe. They're all at this sharp boundary between oxidized clastic rocks and oxidized arenaceous rocks and organic rich shales and carbonates. So.
Thank you both for your comments. I liked your map of Pangea. It was very helpful and interesting. Thank you for that.
Well, thanks. Thank you, David. Well, yeah.
Raises an interesting question, John. That big map of yours, where you've got all the countries sewn together. I didn't see any references there, but I'd like to know, quite frankly, how you did put all that together, because each one of those sections represent about 100 graduate student projects, and how you could put all those together into that form. I'd like to know more details about it. But
it's called the web.
But that's very difficult to do the way you sewed that together.
I didn't sew it together. I think you're talking about the big.
Yeah.
globe with it. Yeah. No, I downloaded that from the web today. I realized that I didn't have a good enough map of Pangea while I was rehearsing, and went on the web and happened to find it and thought,
Okay.
my gosh, this is a great thing.
Yeah. Do you remember what reference that was?
I can give it to. I can look it up and give it to you. Yeah.
That's okay.
I have it written down somewhere.
Uh,
Yep. So, yeah.
No, it's all very interesting, though, John. Very interesting.
The things that I drew myself with the flattened sections, the flattened cross sections, that's my work, and I take responsibility for any gross errors.
Okay.
So,
Do you have any observations on the Grenville Front Mid-Continent Rift relationship? Because they happen in such a short period of time where you've got this, major rifting event, some of the thickest rift fill sequence in the world. Then you have the Himalayan style continental collision in close proximity in short time difference.
I don't personally understand that. Because the mid-continent rift is not at all a typical failed arm. It's curved. It's got this thick igneous fill as well. So I'm not quite sure what was going on there at all. Almost every other contemporaneous thing like that I can think of is more or less straight and wedge shaped. That's true of the Benue Trough. It's true of the Anadarko Rift, and it's true of rifts that I know of in Australia too.
Thanks.
That very odd curve, isn't it, on the mid-continent? Oh.
All right. Do we have any other
Oh yeah,
questions?
we got a question about gold or pegmatites in the Coal Creek amphibolites. There's no gold that I'm aware of. I think there was one gold prospect that didn't amount to anything in the hill country, and there are some rare earth occurrences, but I don't think they're in the Coal Creek. In fact, I'm sure they're not.
Well, yeah, there are some, but they're all underwater now.
Yeah.
So,
yeah, destroyed by the damn builders. So, okay. Any more questions?
No, I just have a comment. Thank you very much, John. That was very informative, and your graphics were excellent. So thank you for sharing.
Well, I couldn't have done this by myself. I got a lot of help from www.
don't we all?
Thank you.
Yeah. Let me add that we're going to be making announcements on the field trip coming up to West Texas pretty soon. So just watch the AIPG-text.org website for additional information.
I think that's going to be a wonderful trip, and it's an area.
Yeah.
I've been on field trips in the Big Bend Ranch and Big Bend National Park, but this Van Horn, West Texas Panhandle is an area that I'm very unfamiliar with personally, and we'll be looking at things like rare earth deposits there. So.
All right. Well, if we don't have any more questions, we thank you all for coming. John, thank you for an excellent presentation. And we hope to see you in upcoming. We're going to have one every month with the Texas section. So please register and look at what's coming up in the upcoming months. So thank you, everyone.
Okay. Thank you, John.
Thank you. Thank you,
Well done.
everybody, for coming.
Well done.
Thanks.